Okay, so what we did last week, we reached to tutorial 2 in chapter 2. This is the first tutorial in the chapter, and it is about translational systems. All the problems are about translation systems, in which we solved for the free vibration to find natural frequency of a single degree of freedom system that can be modeled as a spring mass system. So some of the problems are given as spring mass system. Some of them can be modeled as a spring mass system. Okay, so we have we reached up to question number 7. Okay, number 8 is a spring mass system with mass 2 kilogram and stiffness 3,200 Newton per meter. Has a zero initial displacement. What is the maximum initial velocity that can be given to the mass without the amplitude of a free vibration exceeding a value of 0.1 meter? Okay, so this is the spring with mass. So it is a spring mass system. We have zero initial displacement. So x at 0 is 0. Then the question is, what is the maximum initial velocity? So we have a zero initial displacement, but the initial velocity is not 0. And the question is to find the initial velocity so that the maximum amplitude will not exceed 0.1. And then from the response equation, we know that the amplitude in this case is equal to x dot at 0 divided by omega n. Okay, that is the amplitude. Okay, x dot at 0 divided by omega n. And we make this equal to 0.1. Okay, omega n is obtained from the mass and from the stiffness, square root of k over n. And then from this we can find x dot 0, right, which will be 0.1 times omega n. Okay, and that will be, the answer to this equation. So it will be x dot at 0, which is required, is 0.1 omega n is square root of k over m. And then you can put the values for k and m and find the answer. Okay, question 9, find the response of a spinning mass system with mass 1 kilogram, stiffness 4 Newton per meter, x0 equal to 1 millimeter. This is x0, it means the initial displacement, x at 0. Sometimes we write it this way. And x dot 0 is square root of 5 millimeter per second. Okay, again, the initial velocity is sometimes written this way, x dot at 0 or x dot 0 equal to square root of 5. The question is to find the response, and the response is x of t. Okay, and for a spring mass system, okay, the mass is 1 kilogram, stiffness is 4 Newton per meter. You can, first of all, you find omega n. Okay, which is omega n equal to square root of k over m. And this will be 2, right? 2 radian per second. And response, which is x of t, is equal to x dot at 0 divided by omega n sine omega n t plus x at 0 cosine omega n t. And this will give you the response. Okay, because we have initial displacement and we have initial velocity. Then the question is saying evaluate the peak amplitude and the phase shift. It means we put this into A0 sine omega nt plus phi. Okay, so this is required. This is called amplitude or peak amplitude, and this is the phase shift. Okay, calculate the displacement at t equal to 1 second and 1.5 second. Okay, here we need to put the when you substitute for t equal to 1 second, it means you will have x dot at 0 is the square root of 5, omega n is 2, so it is sine omega n, and omega n is 2 times 1 plus 1 millimeter cosine 2 times 1. So in order to evaluate the sine and cosine in the calculator, make sure you put it in radian. So those values, this is 2 radian. Okay, 2 times 1 is 2 radian. And then in the calculator, you put the mode on radian to evaluate the amplitude at t equal to 1 second. Okay, the same thing here. This is in radian. And then at t equal to 1.5, you will do the same thing. Okay, and find the amplitude. Then sketch the result for at least 2 periods of oscillations. You can do this when you find the phase. You will see how from where to start. Okay, so suppose we have this is 0 phase, which is sine wave, 0 phase, and if it is cosine, okay, it is 90 degrees. Phi is 90 degrees. See how much is the phase, and then you can see how much you can from where to start. Okay. Okay, so this is all of the questions in the tutorial. Okay, and we finished this part, which is the translational system. This is the second type of problems will be about rotational vibration that can occur in shafts or you have torsional spring. Such a system is modeled as shaft, as you can see here, carrying a disc. Okay, this is the disc is rigid, and it is fixed with the shaft on this point. The shaft is fixed from the other point, and we assume that the shaft is massless and that the mass is only the mass of the disk or any object, but this is our model. Okay, it can be any other object. The shaft is a circular diameter, has a circular diameter made of some materials, and which has a modulus of rigidity, G, and also a length, L. Okay, so you see this one or not? This is L. This is the length of the shaft. The shaft is going to provide, if the disk is allowed to rotate with angle theta, and the type of motion here is only about the axis of the shaft, about the center line. Okay, this is the axis of rotation. There is no swinging here. There is no, like a pendulum. It is, the swinging can be in 2 directions, but this is all ignored. We have only twisting type of motion or rotation. Twisting, as you did in mechanics of material for shaft and rotation, you consider twisting. Okay, so this is only twisting. This type of a twisting in this course is oscillatory type. Like the spring mass system, it is oscillatory motion. The twisting here is also oscillatory, so theta is function of time. Okay, this theta is angle of a twist, but it is function of time, just changing with time. Okay, the rotation is occurring about the axis of the shaft. The disk is uniform and with mass m, but what is more importantly in the disk in rotation is the mass moment of inertia, Jo. Okay, Jo is the mass moment of inertia, or polar mass moment of inertia, to be more specific, which has the unit kilogram meter square. Okay, so this occurs in machines with rotating elements, a shaft or impeller, carrying impeller, or a shaft carrying rotors, so they can vibrate into torsional vibration. Okay, so Jo is polar mass moment of inertia in kilogram meter square, and theta is the angular rotation or displacement of the disk. It is also the represent the angle of a twist of the shaft, and this is an radian. Okay, we have other dimensions h and d. If this is a uniform disk, then Jo is equal to 1/2 m r squared. Okay, r is the radius, so d is 2r. Okay, for uniform disk as shown here, this is a disk with a uniform height h and a diameter d, and then you can find the mass from the volume, and if you know the density, you can find the volume. The mass from density and volume, or if it is just given the mass, then you can use the mass. It is half mr squared. Okay, that is the for uniform shapes. Okay, you can calculate as you did in statics the moment of inertia. This usually what you did in statics was for areas are given for certain shapes, regular shapes. Okay, otherwise you need to do the integration, or you use radius of gyration. Okay, so J is also written as Ko square times M. So for the radius of gyration, in this case, equal to r over square root of 2, right? So you can usually we use the radius of gyration of more complex shapes. Okay, that can usually they are found experimentally. The moment of inertia, or complex shape that we don't have the equation straightforward like half mr squared. Okay, from the theory of torsion of circular shaft, we have the relationship between the torque applied and the angle of a twist. That is mt is the torque and theta is the angle of a twist. We have G equal to GIO over L. Okay, where G is the modulus of rigidity or shear modulus. IO is the polar moment of inertia, but note that is Jo is the mass. Okay, this is the difference between Jo and I. This is polar, Jo is polar mass, yani kilogram meter square, and that is for the disk. And IO is the polar moment of inertia, which is the second moment of area, given in meter to power 4 of the shaft. Okay, and for a circular shaft, it is IO equal to pi d to the power 4 over 32. This is in torsion. It is about the axis of rotation. Okay, and L is the length of the shaft. And this relationship, you can see that G and IO over L. IO is the geometry dependent of the cross-sectional area. And if this is constant, if you have a uniform shaft, and L is the length. So this part, okay, this expression is constant and represent the stiffness. Okay, stiffness of the shaft, because the shaft, the type of loading of the shaft is torque or torsion or moment, and the relationship between the torque and theta is linear. This is similar to the Hooke's law for the spring, that F equal to K times X. Here we have the torque equal to K times theta. Okay, so this K is the torsional stiffness. Okay, thus the shaft act as a torsional spring with a torsional spring constant Kt, and T is for torsion, equal to mt over theta equal to GIO over L. And when we substitute for IO for a solid circular shaft, we have that Kt equal to pi G d to the power 4 over 32L. Okay, so then you can get the equation of motion from the free body diagram. Okay, you draw the free body diagram for the disk, and in free vibration that there is no force or torque applied on the disk, but the only torque is resisting the motion is provided by the shaft. Okay, the shaft is torque is equal to Kt times theta, which is mt. Okay, we call this as mt. Okay, equal to Kt times theta. So that's the only moment trying to restore the motion back to the equilibrium, but this is the shaft is acting as a torsional spring, so this will keep oscillating. Okay, so the equation of motion will be that sum of moments. We use sum of moment here, which is the Newton's second law, but in other form, rotation. That is sum of moment equal to. Let me write it here. Okay, so Newton's second law. And rotation is that sum of moment about the point O, which is going through the center of rotation, axis of rotation, equal to JO theta double dot. Okay, this is the Newton's second law. And the moments we have on the left-hand side of this equation, we sum all the moments. We have only the restoring moment of the shaft, which is minus Kt theta, minus because the direction of theta, as you can see, if you look from the top, is clockwise. Okay, theta is clockwise, and the shaft is going to provide a restoring moment in the opposite direction of theta, which is counterclockwise. So with the assume positive direction is clockwise, then we have minus Kt theta equal to JO theta double dot. Okay, retaking everything on one side, we have JO theta double dot plus Kt theta equal to 0. So that's the equation of motion. And it is a second order ordinary differential equation. Same as what we get for the spring mass system. This is second order ordinary differential equation with constant coefficient, and it is homogeneous, except that we have the parameters now are different. Okay, instead of x, we have theta, but we have second derivative, right? As you can see, x theta double dot. And instead of mass, we have mass moment of inertia Jo, and instead of k, we have kt. So it is the solution, or the nature frequency is obtained the same way we did with the spinning mass system, because this is the when you divide by Jo, then you get theta double dot plus kt over Jo theta equal to 0. So this is the final equation after dividing by Jo. The coefficient of theta is omega n squared. Okay, so this is the omega n squared. Okay, this is in analogous to the x double dot plus omega n squared x equal to 0. So they are similar. And we reach the same observation that the nature frequency is the coefficient of theta. Okay, which is omega n equals square root of kt over Jo, and we can substitute for kt as g d to power 4 pi g d to power 4 over 32L. Okay, that is kt. And also you can find the period of oscillation and the frequency in cycles per second, the same way we did with the spinning mass system, that tau n is equal to 2 pi over omega n, which will lead to 2 pi square root of Jo over kt, and that if n equal to 1 over tau n, and this will lead to if n equal to 1 over 2 pi square root of kt over Jo, if n is also equal to, omega n equal to 2 pi if n as well. Okay, so those harmonic relationships we already obtained before and also applicable here. Furthermore, what we did in maximum velocity, the equation for theta, the solution, if you want to say, okay, as we did, solution of the differential equation will be theta as function of time is going to be theta dot at 0 divided by omega n sine omega nt plus theta at 0 cosine omega nt. Okay, you remember this equation we obtained for the spinning mass system. So just to compare, it was x equal to x dot at 0 divided by omega n sine omega nt plus, okay, plus x at 0 cosine omega nt. Okay, so we are getting the same solution, but except that we mean here, the solution is for theta rather than for x. Okay, also you can write this as A0, but this A0 in radian, sine omega nt plus phi. Okay, but A0 is in radian, and when we did the same similar thing for x, it was A0 sine omega nt plus phi. A0 in meter or millimeter. Okay, so the same equation, the same responses, response equations, but the units are different because the differential equation is the same. So if the question is to find the response, you can use the same equation, and if the nature frequency is required, then it is square root of kt over Jo. Okay, and the same thing if you want to find theta for at a given time, then you will substitute with t, the given value of t, and adjust the calculator mode to radian. Okay. All right. So let's move to the example. Example 5, an automobile wheel and tire are suspended by a steel rod 0.5 centimeter in diameter and 2 meter long as shown in the figure below. Okay, so the figure, this is the shaft which has L equal to 2 meter, which is long, 2 meter is, and the diameter is 0.5 centimeter. So it is a small diameter compared with the length. So this will be easily to twist. And it fixed at the top and carries the wheel and tire assembly. Now the wheel and tire represent like the disc. So it is uniform that it is supported, at the center, and it is uniform so that the center of gravity is at the location of the shaft. Okay, but it is not a disk that we can calculate the moment of inertia Jo equal to half mr squared. So it is we cannot use half mr square here. Okay, because this is not a uniform disk. So one way to find the moment of inertia of the disk, of the assembly, is by conducting an experiment. So you can support the wheel and tire assembly with the shaft. Okay, you make the shaft long so that it will be noticeable. The rotation, it will be noticeable. You can observe the oscillation, and you can count number of oscillations, and you can use a stopwatch. So when the wheel is given an angular displacement and released, it makes 10 oscillations in 30.2 seconds. So usually in experimental way to find the nature frequency or to find other parameters, you can take as an average, you take 10 oscillations rather than one oscillation. We know that the period of oscillation is measured for one cycle. Okay, for one cycle, but it will be, if you just consider one cycle, it will introduce many error because the time you measure is using a stopwatch. So you can allow this to oscillate for 10 oscillations, and you record the time for 10 oscillations, then you divide by 10. So the period of oscillation will be 30.2 divided by 10. That will be for one cycle, which is 3.02. 3.02, you might be, you don't get this accuracy if you take the time for one cycle experimentally. So you take for 10 oscillations, and then it will give you the average. Okay, so this is given that, or observe that when angular displacement is given and released, there is no initial velocity, only initial displacement. Then it makes 10 oscillations in 30.2 seconds. Determine the polar moment of inertia of the wheel and tire, which is J. Okay, J or JO it means about the center of gravity, or centroid, about the centroid. Okay, so we know that omega n equal to 2 pi. Okay, this is 10 oscillation, 30.2 seconds. You can find tau n, which is 30.2 divided by 10, because period of oscillation is the time for one cycle. So you can divide this by 10. This becomes 3.02 seconds. Or you can find Fn, which is a number of cycles in second, in 1 second. So this will be 10 over 30.2, which is the reciprocal of tau n. Omega n is 2 pi times Fn, or 2 pi over tau n. So you get omega n equal to 2.081 radian per second. Okay, so that is experimentally, but it is calculated from the measured time and measured number of measured time for 10 oscillations, and then you can calculate the natural frequency. So there is no direct way to measure the frequency. Okay, so you measure the time, and then you can calculate the frequency from the equation of the natural frequency, taking either omega n equal to 2 pi over tau n or equal to 2 pi Fn. Okay, so this is calculated, but from experimental values. The model of this problem is a shaft and a disk. So omega n, this is uniform, and then omega n will be equal to square root of kt over Jo. Here it is, Jo is just called J, and kt is just called K. Okay, that's just different from different source or from different textbook. They use different names for the stiffness and for the moment of inertia. Okay, so kt or K here. So we have kt is given as capital K. Okay, or and that Jo is equal to J. This is unknown. Okay, regarding K is the shaft informations are given. We have, this is a steel. Okay, this is the material of the shaft, and it is diameter is 0.5, and its length is equal to 2 meters. Then you can calculate K from the equation that K equal to Gi over L. Here it's called IP, which is IO, the same. Polar, I mean P for polar, and we use IO for polar as well. Okay, we have IO equal to IP. Okay, and IP equal to pi d to power 4 over 32. Okay, and then we can find IP, which is pi over 32 times 0.5 times 10 to the power minus 2 to convert the centimeter to meter to power 4, and it's equal to 0.006136 times 10 to the power minus 8 meter to power 4, and then K equal to G I over L. So it is 80 times 10 to the power 9, G for steel. Okay. G for steel is 80 gigapascal. So it is 80 times 10 to the power 9 times 0.006136 times 10 to the power minus 2, minus 8 divided by 2. 2 is L, the length is equal to 2.455 Newton meter per radian. And then we can substitute to find J, which is K over omega n square. Okay, we use this model. Omega n equals square root of kt over jo. You put jo on one side. You square both sides of the equation, and then you can find jo, which is equal to k over omega n squared. It is 2.455 divided by 2.081 squared, and GO becomes 0.567 kilogram meter square, and that was the required thing. Okay, so this table we talked about in tutorial 2. If you have springs in series or you have springs in parallel, you need to get the equivalent stiffness and model the system as a spring mass system. This is a torsional spring, and either it is KT is given or the parameters are given. You can calculate K. Okay, this is the shaft and twisting. Then this is what we did today. That is K equal to G J over L. Okay, the rest, most of them we know. Okay, so if you have no questions, I will move to example number 6. Okay, which is related to rotational vibration. The torsion and rotation, it means we have theta, but torsion is usually torsion of shaft. Rotation, it means like a pendulum or pivoted bars, as in this example. Example 6, the figure is shown, and the figure below shows a uniform bar pivoted about point O with springs of equal stiffness K at each end. The bar is horizontal in the equilibrium position with the spring forces P1 and P2. Determine the equation of motion and its natural frequency. Now we have the bar is rigid, and it is in rotation about point O, which is non-centroidal point. Point O is not on the centroid or on the center of gravity. Okay, so we have for the center of gravity is moving in translation, the whole bar is in rotation. So this is not translational problem, and since this is non-centroidal, we have also that the center of gravity is in translation as well as the object is in rotation. It's like general plane motion, or we call it non-centroidal rotation. That is more accurate. Okay, we have the equilibrium, as mentioned, is the horizontal position of the bar. The bar is rigid. It is not flexible. We ignore the flexibility so that we limit the degrees of freedom to single degree of freedom. One coordinate is enough, which is theta, because the bar will stay will stay straight during vibration as well. So this is it's not going to bend, and this makes the problem as a single degree of freedom system, and it is rotating about the pivot point only. The equilibrium position, if you take the equilibrium, the bar is horizontal and it is pivoted at point O, and you put the forces. We have the weight. Okay, we have the weight at point CG, which is a distance C from point O, and then we have reactions. You can add, reactions OX and OY. Usually we don't add them because we will take comment about point O, say they will cancel out. And we have the forces P1. Okay, the forces and the springs for equilibrium, you can assume that both springs are under compression. So it means that the forces will be P1 upward and also P2 is going to be upward. With this assumption, we have no information about the type of or the values of this of P1 and P2, or whether the springs are under tension or compression. As you know that with the spring mass system, that the equilibrium position will cancel the weight. So we don't put W in the equation, or it is not part of the equation of motion. So that K delta equal to mg. So here we are trying to do the same thing. And whether you assume that the springs are under tension or compression, or that one is under tension, the other one is under compression, it will not matter, because it will the equation in equilibrium will always be satisfied, and it will cancel out, and it will be eliminated from the vibration equation. Okay, so assuming that the springs are in compression. And if they are under compression, it means their effect on the bar is upward, right? As shown here in the figure, that P1 is upward, P2 is upward, okay, and the weight, of course, is downward. Now we take the sum of moment about point O. This equal to 0 because we are doing the equilibrium. Huh? So sum of moment equal to 0. This distance is A. The whole distance from the end to the pivot is B. Then moment about O is equal to P1 times A plus mg times C minus P2 times B equal to 0. This is the equilibrium equation. For the vibration equation, or state, we will use that the horizontal is the equilibrium position, and the rotation is about point O, so this will take an angle. This is point O, and this angle is theta. This angle is theta, and also on the other side it is theta because this is rigid. Okay, the springs, this is the assumption we did, that they are under compression. Okay, we will put the weight mg at a distance c from O, and the spring on the, okay, this is the amount of going upward. Okay, how much is this distance? You can draw a right angle triangle, and you will find that this distance is A, because this is A. Okay, the whole thing is A, right? This is the bar. A sine theta. And this distance will go downward and equal to B sine theta if you just complete the right angle triangle. Okay, this might be a bit longer. Okay, and a bit longer here on this side. Okay, so this is the vertical deflection on the other side. Okay, we have B sine theta and we have A sine theta because the angle is the same on for both. Those are similar triangles. Now, with the assumption that the force is, we'll assume that the spring is still under compression, as we did in the statics. This is under compression, so it is going to be upward. But this force will not be P1, it will be P1 less than P1 because the spring is opened. You know, if the spring is under compression, it is under compression, it means there is a force P1, right? If you open, this is the force is P1. If you open it or release it, okay, then it will be still under compression. This is the, let me just take, this is the L0, okay, uncompressed. Spring. So the force is what? The force in the spring equal to 0. Here it is compressed with the force on the spring equal to P1, right? This is also compressed because it did not reach to this height, okay? But it is, the force in the spring should be less than P1, right? Because this is compressed more. The first state here is compressed more than the second state. So the force of the spring is not 0, but it is less than P1. How much is less than P1? If you know this distance, then you multiply K by this distance, that will be the amount to be subtracted from P1. So for this case, we have P1 minus K times A sine theta, because the deflection we have is A sine theta. The spring on the right side, right end, is compressed more. Okay, so it means the force in the spring is more. This is P2 plus K times B sine theta. Okay, so this is the case for spring P1. For spring with P2, let's say this was the height or L0 with spring force is 0, then it is compressed, okay, with force in the spring equal to P2. It is compressed more, then the force in the spring is greater than P2. Okay, and how much is greater? Then we have to calculate this distance, or we know this distance plus multiply by K. Okay, so this distance is X multiply by K. It's going to be the additional force in the spring to be added with P2. Okay, so this is the free body diagram. Okay, in vibration. One more thing we can do is assume that the vibration is about small oscillations. So this will be, you can use that for theta very much less than 1, you can use sine theta is equal to theta, and cosine theta is equal to 1. So this will reduce to A theta, and this will reduce to B theta, and this equation or this force becomes P1 minus Ka theta, and this force becomes P2 plus Kb theta. Okay, the distance here is A cosine theta becomes A, and this distance is B cosine theta becomes B with the assumption we are doing. And then the equation of motion is obtained by Newton's second law, sum of moment about point O equal to JO theta double dot. The moment is clockwise positive because the direction of theta is taken clockwise. Then we have P1 minus K A theta times A plus mg times C minus P2 plus KB theta times B equal to JO theta double dot. And when you open the brackets, you can see that P1 times A plus mg times C plus P2 times B, you can group them together. Minus, there is somewhere is minus here. Okay, minus Ka squared times theta minus K B squared theta equal to JO theta double dot. And this will equal to 0. Then the final equation will be JO theta double dot plus, you can take theta common and K common. So this will be K A squared plus B squared times theta equal to 0. This is the differential equation. You can divide by JO, you get theta double dot plus K A squared plus B squared divided by JO theta equal to 0, and this is the final form of the differential equation in which the coefficient of theta is omega n squared, or omega n equal to K A squared plus B squared, okay, divided by JO. Okay, this is the equation for the nature frequency. Okay, so this is the equilibrium equation. This is the equation in vibration. Using the equilibrium equation, this will reduce to theta double dot plus Ka square plus B square over JO times theta equal to 0. And then by inspection, there is no, you are not solving differential equation, you are by inspection. This is second order ordinary differential equation. The coefficient of theta is the nature frequency squared, or you can get the nature frequency. Okay, any questions? Next time we will.
دكتور.
Yeah.
شلون عرفت ان الثيتا from both sides بالنسبة للبار والهوريزونتال نفس الشيء؟
Okay, because this is rigid. Okay, I didn't add this. Okay, this is a rigid bar. It's not going to bend. This is one of the assumptions also.
دكتور يعني حتى لو البيفت صاير مو على السنتر اوف جرافيتي؟
اي حتى لو مو صار على السنتر اوف جرافيتي because this is a straight line. في تقابل، لا تقابل في الزوايا. Opposite.
تمام اوكي.
Okay, so we'll see you inshallah next time. مع السلامة.